Mr. Sams? What are you doing?
What do you mean?
It looks like you're sticking styrofoam balls onto your face.
I am.
And that would be because...
And onto the rest of my person.
And they're falling on the floor.
I'm making them bond to me. I'm making chemical bonds.
Bonds. Chemical bonds.
Yeah, sure.
That is what we're going to talk about this time. We're going to be talking about chemical bonds.
Came off.
So people, Mr. Sams obviously needs help.
I need more tape.
He needs more tape. He needs more help. He needs more help to do this. So I think you need professional help. I have a counselor friend.
Oh yeah?
Yeah. Maybe I'll get Miss Wilson in here to come help you because obviously you need some deep counseling.
Nah.
Yeah.
Just bonds.
Yeah.
Chemical bonds.
Well, I guess we are talking about chemical bonds.
We
so
are.
I guess we should probably start talking about chemical bonds.
All right.
Okay, let's do that. Well, seriously, folks, we really are going to be talking about chemical bonds. And Mr. Sams, as crazy as he is, we have no idea where his brain is today.
I don't know what you're talking about.
So, podcast 8.1. Types of bonding, electronegativity, bond polarity, dipole moments, ionic size. We're going to talk about all these things. All right, so this is the beginning of Chapter 8 in AP Chemistry, using the Zumdahl text, by the way. And that would be the 6th edition. You got styrofoam in your mouth.
Yeah.
What were you eating?
I was not eating styrofoam balls. It was out of my mouth.
You need help, folks.
I've been hanging around
Listen
with my 1-year-old daughter
carefully. He needs desperate help.
Anything that's on the floor.
Miss Wilson, come save us. Okay, so here is the schedule for everything for this chapter. 8.1. This is actually these sections in the Zumdahl textbook. Even though we call it the 8.1 podcast, it actually is like 8.1 through 8.4 in the Zumdahl book. Okay, so with that said, let's talk about bonding.
All right.
Folks, do you realize there are 3 main kinds of bonding? And many of you have seen a chart like this before, but we're going to talk about this. There is ionic bonding, there is covalent bonding, and there is metallic bonding.
And then there's tape.
And then there's tape. There you go. Ionic bonding, what's the story on ionic bonding? That is a bond between a
metal and a non-metal.
A metal and a non-metal. Covalent bonding is a bond between
2 or more non-metals.
A non-metal to a non-metal. And a metallic bond would be a metal.
Metals.
And then covalent bonding has these things called polar, non-polar, and that's a London dispersion force, hydrogen bonding, dipole forces, and we're going to get into this in great detail as we progress in this particular unit. This unit, by the way, encompasses chapters 8 and 9 and then part of 10 in our textbook. So that's where we're going to kind of finish up with. Now, we want to first start talking about what holds everything together.
Tape.
Tape. There you go. Tape holds everything. Duct tape.
Duct tape specifically.
Yes, indeed. We've got our peanut gallery over here. Isabeau's helping us out today. Okay, and the key thing actually, it's not tape that holds everything together.
Really?
No, it isn't. It's actually Coulomb's law.
Oh.
Yeah, there was this dude named Coulomb, and he made a law. And they called it Coulomb's law. Yeah. And basically he said that if you have 2 things with charges, and Q here stands for charge, Q1 and Q2. And then R is what?
The radius or the distance between them.
So you have 2 objects that are close together. They are attracted together with a particular amount of energy equal to KQQ of R, where the value of K is this particular number. And the Q is like the charge. So if I have, for example, like sodium and chloride, which is Na positive and Cl negative, Q1 would be positive 1 and Q2 would be a negative 1.
Negative.
And hence that gives you the answer.
I guess there's no T in there, so there's no tape term.
I don't see T's in there.
No. Okay.
I'm thinking not.
All right.
So what actually holds things together is...
electrostatic attraction? Is that the word you're looking for there?
That is right.
All right. There's static in tape. Yeah. If you put 2 pieces together and pull them apart, you get all staticky, right?
There you go. And then you can create this electrostatic attraction.
Okay.
But basically what electrostatic attraction means is that positive things are attracted to negative things. Now, why is that, Mr. Sams?
Because opposites attract.
Why do opposites attract?
Makes life more interesting?
Yeah, I guess so. The actual answer is, from a scientific perspective, is we really don't know.
Yeah.
This is where string theory comes in and all this interesting stuff that basically, why is that the case? And of course, you probably also know, if you ever play like a magnet, if you take a positive thing and a positive thing, they actually repel. Why is that? We really don't know.
They just do.
They just do. We do not know the answer to that question. It's one of those questions of why are the fundamental forces, and we don't know.
We don't know.
But we can measure it, we can use it to calculate things, etc., etc. So we know the strength of it, but it's an interesting thing. All right. Let's talk about ionic bonds, okay? Now, in an ionic bond, not diagram, just ionic bonds, what do the electrons do?
They are transferred from one atom to another atom.
So that's the key thing in an ionic bond. So now we're going to focus a little bit on ionic bonding for a few minutes. Is in an ionic bond, there's a transfer of valence electrons. Actually, I need a blank page, so hold that thought. All right, so what I'm talking about this is when I have a... All right, so if I've got sodium, sodium has one valence electron.
Yes, it does.
Now, we haven't really done Lewis dot structures, but most of you have seen this kind of a concept before. And say chloride has 7 valence electrons. Okay?
And everybody wants 8.
Remember that rule of 8, octet rule. And so the sodium wants to give away 1 electron, so he ends up with 8. I know it sounds like he'll have 0, but actually have 8 on the center layer.
Yeah, the next layer down.
If you were to draw a sodium ion, or sodium atom, you would have 8. This would be what one of the shells, and then another shell would have 1.
That's where the 1 is, yeah.
And that's the 1. And this is the 1 that's going to be given over to the chloride. And then the chlorine, actually the chlorine wants 8. And so when everything is done, when he loses an electron, something happens. What happens?
He gets a positive charge.
Now, why does he get a positive charge?
Because electrons are negatively charged.
Well, Mr. Sams, I have a problem.
Oh, you have a marker on your head.
Well, it's actually an electron. Oh,
let me help you.
I gotta help
Hang on a sec.
Ow!
There.
Oh! It's in my eye. Okay, we got it. All right. So I have a problem.
What's your problem?
I have a marker stuck in my head.
Yes, you do.
But it's an electron. And you see, I do not really want this electron.
Okay.
Because you see, I have an extra electron, like the sodium atom.
All right.
Got the idea?
Okay.
And you really want...
I want that electron.
You're the tape guy.
Yeah.
You're the tape guy. So what would you do if you were like a chlorine atom?
I'm going to try to get that marker and I'm going to tape it to my head.
I think you actually need to take it.
I think I'm going to take this marker. Ooh,
and put it on you.
I don't want your nose grease tape.
Oh, have mercy.
I'll get my
own
nose grease.
Really, really good. Because you see, I wanted to get rid of that electron. And guess what happened? You wanted to take the electron.
I did. Now I'm going to take it and tape it on my nose.
You see, by the way, you know when I had that nose? My nose with the marker on my head. I didn't feel very positive about myself. I felt pretty bad.
Because you see, marker on your head?
Because electrons are negatively charged, and so when I gave you my negatively charged electron, or you took it, I feel really good about myself.
So you feel?
I feel positive. And of course, you took my electron away from me, so you feel
negative. I'm feeling kind of guilty. Yeah, so.
You're feeling pretty bad that you took it.
That I took it.
Yeah, and you get the idea.
That I look pretty ridiculous.
So, folks, you get the idea.
Yeah.
He took the electron from me.
Yep.
And now he feels very negative because, of course, he looks ugly. He's ugly anyways. And so you see, I feel positive because I got rid of the ugly nose. Now he's the ugly one. I was ugly, now he's ugly. You get the idea? All right, I think we get the idea.
And I got to use tape, too.
Okay, so Mr. We're back again live on Therapist. Okay, so what actually happens is the sodium then, picture 1, and we have picture 2. The sodium now has a positive 1 charge. That was me, of course, the good-looking guy, because I feel positive. At least I felt positive. And Mr. Sams gets that extra electron. So instead of having 7, he now has 8. And here's the 8th one right there. And he has a negative charge. Now, what happens now with the sodium? Why does the sodium connect to the chloride?
Because opposites attract.
Yeah, so positive attracted to negatives. Actually, if we would have taken our analogy further, we should have hooked up together. And that sounds wrong. Yeah, that is wrong. Okay, covalent bond. Now, in a covalent bond, something else happens. What goes there? That's called
that's where they're sharing.
Oh, it's a very nice. It's like when in kindergarten you learned how to share. So they share valence electrons. And when they share, we could say, for example, take chlorine and say chlorine. So chlorine has, as you call, Jim, just a minute ago, 7. And you see, they want to have 8. And so if they could share that extra 1, maybe a circle around all of them, he now has 8. And if I go like this and he shares that one, he has 8.
So, and then the overlap is going to be the covalent bond, the sharing of those 2 electrons.
So you would actually draw it like this. You'd say Cl line, Cl. Now that line, this line, is equal to those 2 electrons that are shared. And then you would have the additional electrons. And now we haven't done Lewis dot structures. I believe that's the next podcast or something subsequent. But I want you to get the idea. They share, and that's what makes the bonding.
Sharing is caring.
Share. Like to share. And lastly, we can have a metallic bond. And a metallic bond is where we have a C of valence electrons.
Not the letter C, and SEA, like the ocean.
Like the ocean. And basically what you've got here, pictorially, is you have you have a piece of metal. All right. And the piece of metal has, in the center of each atom, a nucleus.
Positive nucleus, yes.
A positive nucleus. So to help illustrate a metallic bond, Mr. Sams is holding up a...
Do you remember the baseball bat from last time?
Why isn't it not in my hand?
Yeah, because, you know...
I hit you over the head last time with it.
Vengeance and, you know, paybacks and stuff.
All right, so if we take a look at this aluminum baseball bat, it's held together. Yeah, there's lots of different metal atoms in the baseball bat. And so if you look at this particular thing, there are lots of little positive charges. And those positive charges, somehow this piece of metal is holding itself together since it is, well, since it's a metal.
It's together.
Yeah. So if we look back on the screen, think of this as the big piece of aluminum, and then we've got electrons. Now, one thing that's true about a metallic bond is, or about all metals, pardon me, is that the electrons are free to move around the atom.
That's why they're good conductors of electricity.
Yeah, you wouldn't want to stick the baseball bat in the electrical outlet. That would be a bad day.
I'd have a hard time doing that.
And so since these electrons are free to move, and they don't actually live with a particular atom, they are kind of, it's like a commune. They
delocalized.
Yeah, big fancy is they're delocalized, means they, what does that mean, delocalized, Mr. Sams?
They are not in a particular locale.
And so if you kind of look at this chart here, the way it is, this area right here on the graph has a charge that's roughly negative, doesn't it? And since there's less electrons over here, this area over here is positive. And guess what? Positive things are attracted to negative things, and that's what holds it together. So just the random motion of the electrons causes that metal to stick together. Okay? Now let's talk briefly about a covalent bond and bond distance. This is really not that, this looks more complex than it actually is, and people get kind of confused by this. But basically, if you take... Actually, maybe we should do a diagram of a covalent. Well, they do have it here. They've got two hydrogen atoms, and then these little red dots here represent the possible locations of an electron. Right. Remember we talked about the quantum mechanics things. And as you get them closer together, actually, if you think about it, that would cause them to want to repel because electrons have the same charge, and that would cause them to repel. But there's also an attraction of this electron for this positive nucleus. Mm-hmm. And so that's what is drawing this atom together, and this nucleus is attracted to, say, this electron. So as you draw them closer together, so if they're far apart, they're very separated out here, and then we come across on this graph closer and closer, you reach a point where they have the minimum amount of energy, which makes it the most stable situation.
And if you smush them too close together, the nuclei actually start to repel each other, so that's why it has some higher energy there.
Yeah, so it reverses here. Now, if you get the nucleus together, the positive parts too close together, then they will repel. And so it's really the attraction of one atom for the electrons of the other is really what's going on. And there's a particular ideal length that has minimum energy. This just happens to be the hydrogen atom, but if I had, say, H bonded to carbon, it would have a similar type of a graph. And you could figure out what that bond length is that way too. All right, that leads us to a concept called electronegativity. What's electronegativity?
It's the how much something likes electrons, basically.
So the attraction of one atom for the electrons of another.
Yep. And as a side note, to have electronegativity value, you have to be participating in a bond. Okay, so you'll notice on this chart here, the noble gases are not listed. There is no value for the noble gases listed because, for the most part, they do not form chemical bonds. So we don't assign an electronegativity value to them.
Yes. So let's illustrate this with a little demonstration. What do you think?
Okay.
All right. So, Mr. Sams, I see you've got a ball.
I do. It's an electron.
And I have a ball.
Hey, look.
And you know what? I'm like that chlorine atom we talked about.
Yeah, and I could be...
my twin. The other chlorine.
The other chlorine.
And so I guess we need to...
share.
Do we share?
Yeah.
So we could share.
So, yeah, we could share the ball. And
but you're like my twin. So.
Yeah, so we both have it the same amount of time.
So the electrons are like shared right equally between us, right?
Yeah.
Oh, okay, cool.
Yeah.
Well, what if I was like... I was a fluorine atom.
Okay, and I'm hydrogen.
Oh, cool. Okay.
Little tiny hydrogen.
So if he's fluorine and I'm hydrogen, hey,
I'm hydrogen and you're fluorine.
I'm fluorine. That's right.
I'm hydrogen.
Okay, that's right.
Yeah.
I'm sorry. I'm fluorine because I'm stronger. You'll see. That's why I picked fluorine. So should we share?
Yeah. Okay. Share. Because form our bond.
Now we're gonna play tug of war.
Yep.
And guess what, ladies and gentlemen? Because I am stronger. I win. The electrons are unequally shared because I am stronger than him. I'm not strong enough to take them, but I am strong enough to share them unequally because the electrons live closer to me.
Yeah.
I am
so he lured me in, like saying, "Yeah, let's share the electrons," and then he's gonna hog them all the time.
I'm gonna hog them all the time.
So that's when the kid down the street says, "Let's play," and then He won't let you play the ball very often. Yeah.
Ha! Gotcha. So back on the screen, guys. Hopefully you figured that out. The whole point here, of course, is that some are stronger than others. Of course, me being the fluorine atom, I am stronger. I have a strength of 4. That's the strongest of all the elements. Mr. Sam's was a mere 2.1. And so the electrons live closer to me than they do to Mr. Sam's. Let's illustrate that with a picture. So he was H, and I was F. He has 1 electron, and I had 7 electrons. If you don't remember how I got the 7, you'll learn in a little bit. And basically what happens is this is sort of picture 1. In picture 2, the H and the F, the electrons are shared, but if you look kind of the way I've drawn them, they definitely live, if this was the center line between the H and the F, they live closer to me than they do to him. And so therefore we could draw the bond as H, F, and we draw it just a single bond, but we'd actually would draw an arrow like this way and put a positive right here and say that the stronger one gets the arrow towards them. Now when we did the chlorine, when you draw the Lewis structure looks like this, and this is where they have the same value. So it was a 3 fighting with a 3, right? If this was a 3.0 and this was 3.0, they are like twins, and so it's an even Steven.
Yeah, I have twins.
Yeah, you have twins at your house.
But they're not identical.
But they're not identical. Yeah, and so in this case, the fluorine was a 4.0 and this was a 2.1, so 4 is stronger than 2.
And Lucy is stronger than Dorothy.
There you go. All right, now.
For now.
At least for now. Now, let's talk about the trend on electronegativity. As you go across, they get larger, so that makes fluorine a highest one, and as you go down, as you can see here on the sign here, they go decreasing. So the lowest one is francium, and the highest is fluorine. So that's how you can know that. And it's really because the fluorine wants the electrons the most, and it also comes back to the size. The size makes a big difference. And so it's got the positive charge. Since he's smaller and that nucleus is close, he's more attracted to the electrons of the hydrogen. So if you ever ask that question, why, for electronegativity, you can answer it. Okay. This isn't a very important one. Okay. That leads us to the concept of a bond polarity. And we've already alluded to this. We just haven't talked about it.
Given it a name.
Given it a name. What we just saw was bond polarity. Actually, let's do polar bond. A polar bond, what is that?
It's when you have a covalent bond and the electrons are shared unequally, just like fluorine and hydrogen did.
Yeah. Unequal sharing of electrons. And then a dipole moment. A lot of people get this confused. On the AP test, they like to use this term for dipole moment. It is when you have a polar substance.
Yeah.
Now let's talk about polar. Well, we haven't got polar yet. Polar bond. Yeah, polar. What does that word polar mean?
Polar means it has an end or 2 ends.
It's got like a positive end and a negative end.
Yeah.
Now one thing we didn't do. Let's go back a couple of slides.
It's like a polar bear has 2 ends, a front end and a back end.
There you go, something like that. Yeah, it does. Yeah, I'm not sure that's why they called it a polar bear.
Is that no what?
No, I think it's because it lives in the polar region of the world.
Oh, I get it.
Yeah, yeah. Now, the point here I wanted to get to is this fluorine, since the electrons are more on this side, and electrons have a negative charge, he has a slightly negative charge. I guess I'm the ugly one now, right?
Yep.
And this little symbol, by the way, means slightly.
Yeah.
And this end is slightly positive.
It's a lowercase delta.
Yeah.
Uppercase delta means change. Lowercase delta means kind of, sort of.
Yeah. So it's sort of negative and sort of positive. And that makes this, if you will, this little bond, a little magnet, where this side is negative and this side is positive, although it's slightly negative and slightly positive. Actually, positive and negative. I did it backwards. But you get the idea, I hope. All right. So a dipole moment is a polar bond.
Molecule.
Molecule, thank you.
Yeah, it's basically just saying that something has a plus end and a minus end.
Yeah, and a dipole just means you got 2 poles. Really, they're all kind of saying the same thing, but I want to make sure you understand that because in the AP test sometimes they use different terms.
Yeah.
And so a polar bond has an equal sharing of electrons. And how do you know if you have a polar bond? Okay, how do you know if you have a polar bond? You have to have an electronegativity difference. You have to use this table here. And do I have any blank white space? Looks like I don't. So let's actually make a little chart here. If you have a electronegativity difference between 0 and 0.4, it's considered a nonpolar bond.
Yeah.
Because that's the chlorine. Because what's the difference between 3 and 3?
0.
0. So that's nonpolar. And then if it's between 0.4 and 2.1, it's considered a polar covalent. That's where there's unequal sharing. And if we did this one down here, 4 minus 2.1, I think it's at 1.9, isn't it? So that would be a polar covalent bond. And if you are higher than 2.1, any number, higher, greater than, this becomes ionic.
Right, it becomes so polar that there's a complete transfer of the electron is essentially what happens there.
The example we gave was NaNCl. So Na has an electronegativity of 0.9, and chlorine is 3.0. 0.9. So the difference there is 2.1. So that's an ionic compound.
I have a question for you.
Yeah.
What if it's exactly 0.4?
Well, that's a tricky question because a lot of people think it's got to be some hard and fast box, and the reality
It's kind of mushy.
It's a mushy system, and 0.4 is sort of ish, and it's really more of it's a continuum.
Yeah.
As you go across this, you get more and more ionic,
Yeah.
or more and more polar, and so it's not like it's just either or. So it doesn't fit in a box in that sense. It's more of a continuum, we would call it.
Yep.
So that's kind of a good question there, Mr. Sams. All right, now. There's polar bonds where the electronegativity is less than 2.1 and greater than 0.4, and there's also a polar molecule. Now, to be a molecule be polar, you must have two things. The bond must be polar.
Yeah.
If you have a non-polar bond, you cannot have a polar molecule. But you also have the shape must not
Cancel out.
And we're going to learn more about shapes in a subsequent podcast. So, but let's kind of get that on the table here for you guys to go that. I guess we should do that now.
Yeah.
All right. So polar molecules. So examples of some polar molecules. The classic example is water, HOH. And I'm not going to. I'll tell you the shapes when we do the shape discussion a little bit later. But water has this bent shape.
Yeah.
And O has a value, oxygen. Let's go
2.4? 3.5.
3.5. So this number here is 3.5, and each of these were 2.1 if you recall. And the difference there is
1.4.
1.4, so that makes it a polar bond.
Yep.
And because of the shape, it's going to cause this to be polar, meaning I put the positive. Actually, what you do is you try and find the center, the geometric center of positive and negative charge. Since the O is more electronegative, it gets a slightly negative charge. The hydrogen slightly positive. And you ask yourself, where's the center of negative charge?
The oxygen.
It would be on the oxygen because, of course, that's the only thing that has negative charge. So this is negative. The geometric center of positive charge is right here in the middle. And guess what? I got a positive here and a negative here. I've made a little magnet, haven't I?
Yep. A little dipole moment.
A little dipole moment, we would say. Yeah. Another example of a. Yeah.
Oh, hey, look at that.
Hey, I actually had a chart here.
Picture.
Picture much better than my little sketch, but you can get the idea. The geometric center is right here for positive and negative here. And notice I have the dipole moment. Actually, notice how the charge is drawn this way. All right. Now, here'd be another example here, ammonia, NH3. Ammonia has a pyramidal shape, and these are the positive ends, if you look. And then if you go right in the center, this is where the center of positive is, and the center of negative charge would be right on the nitrogen, because
it's negative.
And notice that are those in the same place? Is the positive and the negative in the same place?
Oh, no.
So this makes this a little dipole.
Yep.
And then they draw it this way with the little red arrow thing you can see. Now we have a different ballgame with carbon dioxide. See, we have slightly negative, and this is two slightly positives. So where is the center of positive and negative charge? They're actually both on the same place. Yeah. This is positive and negative, and that makes them cancel out. And that makes this non-polar, or not polar right here. Okay? That's not an important screen. All right. We should talk about ions and
We
size.
should, yeah.
Okay, last topic here.
Because it all matters.
Yeah. All right, ions have different...
yes, different sizes than the atom that it came from.
So, if I have an atom...
We talked about this a little bit in the last lesson.
Yeah, if you've got an atom,
this
like
is the babysitter and kid thing.
Sodium, and then I become a sodium ion, turns out this size of the sodium positive 1 is smaller.
Yep.
And so this is actually an example of a cations. Cations are ions with a positive charge. Cations of the same element are smaller.
Because there's more positives in the nucleus than there are negatives outside, so it pulls them in.
And anions of the same element are
larger.
Because
in this case, there's more negatives on the outside than there is positive in the nucleus, so they're spread out further.
So let's say I have nitrogen, and then I have the ion of nitrogen that's most common is the nitride ion, it would be much bigger. So in this case, you've got, your analogy with the babysitters.
Yeah.
Nitrogen has
7
protons, and then you would have 10 electrons. So you've got 7 babysitters trying to hold on to 10 kids, and that's a lot harder than 7 and 7.
Yep.
So that's how you can know that. And there's actually a chart. Draw pictures. We did this. Okay. And here's a chart here. This is the size of the lithium ion and the beryllium positive 2, O negative 2. So the O's would be like small, and for the lithium atom, he would be much bigger than the lithium ion. So the purple ones are bigger than expected. No.
Yeah.
The purple ones are smaller than expected.
Oh, yeah. Sorry, you're right.
And the orange ones, as pictured, are larger than expected.
What's the next slide?
An important word, folks, that's not in your handout that you should add is this word. Everybody write this word. Iso-electronic. Sounds like some fancy electronic part in your computer, doesn't it? But it's not.
No. Iso means same. Electronic means electrons, so we have the same number of electrons.
Okay, so a way to look at this is if I've got a sodium ion, it has how many electrons? So
it has 10 electrons.
How did you get that?
Well, the sodium atom has 11, and the +1 charge means it lost 1, so it has 10.
All right, what if I have magnesium plus 2?
Well, it normally has 12, and it lost 2, so it also has 10.
Oh, same number. That's pretty interesting.
Yeah.
What about, say, the fluoride ion?
Okay, it normally has 9, and it got an extra 1 for the negative charge, so it has 10.
I'm thinking we're seeing a pattern here.
I do.
What about the oxide ion, O negative 2?
Normally has 8, got 2 extras for a total of 10.
Okay.
And hey, let's throw neon in the mix while we're at it.
Neon.
Neon has 10.
Now there's no charge, so you have to play the game.
Right, so all of these have the same electron configuration as neon, and they all have 10 electrons, so we call them isoelectronic. But the difference with these atoms is they have different numbers of protons.
Right.
So, since they have different number of protons but the same number of electrons, they're going to have different sizes. So if we go back to that table and we compare the ones we were just looking at, the sodium and magnesium and oxygen and fluorine, the one that has the least number of protons is the biggest. And why would that be, Mr. Bergman?
That would be because, of course, it has the least number of protons. So it's there's less babysitters holding on to the 10 kids.
Right.
And the smallest one would be, of course, the magnesium, because he's got the most babysitters hanging on to the same number of kids.
Right, exactly.
Or we could even go one more step further. Yep. Aluminum's even smaller. We now have 11.
Yeah.
Yeah, 11.
Yep.
11 babysitters holding on. No, not 11. 13 babysitters
yeah.
holding on to 10 kids. And
we're good at counting.
Yeah, we're really good at that.
That's why we do science.
All right, rank the following order from smallest to largest.
I think we just did.
These are the ones we just did.
Those are the ones we just did.
So let's go back and rank those.
Yep.
So who would be this? Who'd be the smallest to largest?
Smallest would be magnesium.
So magnesium, because he's got the most positive charge.
Positive, then sodium.
So he'd be number 1.
Yep.
And sodium would be number 2.
And then neon.
Yeah, he'd be number 3.
And then fluorine, and then oxygen.
4, and then 5.
Yep.
Yep.
Okay.
That's it. All right. So, Mr. Sams, I think we're done. Pretty quick little podcast.
Yeah, I think so.
Not too bad. So we'll see everybody in the internet land and Ori class, whatever it might be.
Perhaps.
So we will see you all. Have a good day.
Remember to share.
Share. Where's your tape? Just don't put it on me. Don't. Oh, there you go. Not me. What